Welcome back and to the sessions this week, which mainly focus on Hartree-Fock theory, which is our, as we mentioned yesterday, is our first approximation to the full many-body problem. And Hartree-Fock theory functions as a kind of a kitchen item in many-body physics, in the sense that it allows us to redefine a mean field, which hopefully then gives us a better starting point for other many-body theories. And even if we discuss the full configuration interaction theory as the way you would solve the problem in case you can diagonalize exactly, what happens often is that when you run full configuration interaction theory calculations, is that you would have run a Hartree-Fock calculation. And what we showed yesterday is that performing a Hartree-Fock calculation can be interpreted as us performing a unitary transformation on the full Hamiltonian matrix, which we are going to diagonalize when we use full configuration interaction theory. And that diagonalization or unitary transformation zeroes out the blocks which connect the ansatz for the ground state and the one particle, one hole contributions. So let's quickly repeat some of these things. And the equations which we showed yesterday, we ended up with are equations which minimize the energy and hopefully gives a better energy estimate compared to the one where we had a basis which was typical an eigenbasis of the kinetic energy plus this external potential. Now the eigenbasis which we're looking at is actually an eigenbasis of this Hartree-Fock operator. And it's common to label this Hartree-Fock potential as the contribution which comes from the two-body interaction, or perhaps if you have more than two-body interaction, it would also include three-body interactions, etc., etc. But in this course, we're mainly going to limit ourselves to two-body interactions. So the so-called Hartree-Fock potential then brings in an explicit medium dependence due to the summation of all the single particle states below the Fermi level. And it brings also in an explicit dependence on the two-body interaction. And as I say, in nuclear physics and other fields where complicated free-body, higher-body interactions are important, they will also be present. And that will entail some rewriting of this term. And the two-body interaction with its contribution from the other bystanding fermion creates, in a way, an effective mean field. And this effective mean field is a field in which a given fermion moves, in addition to the external potential, which confines the motion of the fermion. Now, you may not have an external potential. So we could have a system which is set up without the external potential, and then just limit ourselves to kinetic energy. So that's fully possible. And we could then have just kinetic energy plus this mean field contribution from the nuclear or the two-body interaction here. And if you look at the systems like nuclei, in which you have no external confining potentials, you would think of nuclei as, for instance, self-bound systems where the binding arises due to the intrinsic nature of the strong force. This is in contrast to what you have in atomic physics and molecular physics and solid state physics, where you often have a potential which confines the motion of the particles. So you could think of an electron in a semiconductor, and there will be a kind of effective potential which is set up by the environment, which confines the motion of the electron. People have actually run experiments where they've looked at the confinement due to even the gravitational force. And there was a very nice experiment which was done in the beginning of the millennium. I think this was done in France, where they actually studied neutrons confined by the gravitational force. And that's another type of many-body problem. But they could actually achieve that experimentally. That's another example of a confining potential. But the standard ones would typically be, if you're studying a system in atomic physics, it would be an electron which is confined by the potential which is set up by the positive ion from an atomic nucleus, for instance, which is then in turn defined by the protons which are present. So the other thing which we did yesterday was to look at variational calculus and we went through some of these details, and I just wanted quickly to refresh some of these calculational details. And what we had then, when we looked at the variational calculus, is that at the end, what we end up with is that we end up optimizing a functional using variational calculus, where we looked at the small variation in the single particle wave function. And that small variation then includes the energy. So the Lagrangian which we're looking at, it contains the expression for the energy as a functional of the trial wave function which we have. And in addition, what we did was to add the orthogonalization constraint. So the function or the functional which we want to optimize is given by a change in the energy and a change in these single particle wave functions. And we end up optimizing this specific problem, and we want to drive this quantity to zero. And epsilon is going to be interpreted as the single particle energies, and, or in total, the energy of the system. And the deltas which you have here are the changes in the single particle wave functions. And we end up with a problem where the epsilons are the so-called Lagrange multipliers. And when we perform the operations, we end up with an equation which looks like this, which then translates into a single particle equation, where we have the kinetic energy, we have an interaction. If we skip the confining potential, we only have this term, but we could also have a confining potential, which the particle moves in. And this is the two-body interaction. And in this case, we have what's called a direct term, and this is the exchange term. So in that way, we are bringing in a type of many-body correlations due to the interaction. But we have a term which here is linear in the unknown quantity. And then we have a non-linearity due to the exchange term. Because the term which we want to solve for is this psi of mu. But you see now that this psi of mu is inside the integral due to the exchange term. And that means that Hartree-Fock theory is an equation which is non-linear in the unknown quantities due to the Pauli principle. If we took away the exchange term and simply neglected the role of the Pauli principle, then we would have ended up with an equation which does not contain these last terms here. We would just have something which will be linear in the unknown wave function psi here. So these are the single particle wave functions which we are changing. And effectively, this is the type of equation which we end up with. And the integration factor here runs over the spatial coordinates and also a summation over the spin coordinates, if you also have spin as a degree of freedom. So these are the Hartree-Fock equation, the way they were solved in the middle of the last century, before people started to use linear algebra method and eigenvalue problems. So this leads to what's called normally an integral differential equation, because you have a second derivative here, which often causes problems, and then you also have to solve the integrals. And normally we try to avoid this type of solutions because the precision of the result depends on the number of integration or discretization points which you have. And if you have the kinetic energy term, you will often end up needing many integration points. So this was the basic equation in what we normally call coordinate space, because we are dealing with the full degrees of freedom in terms of the positions and eventually also the spin degrees of freedom. Now, what we did yesterday was also to introduce second quantization. And in second quantization, we could then actually rephrase this in terms of particle hole excitations. The equation we end up solving, so let's repeat some of the things which we discussed yesterday before we then move on to studies of the stability of the Hartree-Fock equation. Because we can, if we use second quantization, it's also easy to find the equation for the stability of the Hartree-Fock equations. The other thing which we are going to do is also to, besides this discussion here, is to present the computationally efficient method for solving the Hartree-Fock equations. And this normally goes by the expansion in terms of transformation from the basis set, which is an orthogonal one, into a new orthogonal basis set, as you saw in the exercises last week. And you will also see some elements in the exercises this week. And then this is the topic which we are going to discuss in more detail today as well. But let me bring up some of the discussions which we had yesterday. And I'm going to switch to the whiteboard here. So let's do that. So what we discussed yesterday is an alternative to the full coordinate space equations. But what we did then was to assume that this variation, which we did in Hartree-Fock theory in second quantization, we assume then that the change which we had for the this ansatz for the ground state is given in terms of a small parameter eta, which we can actually get rid of. We are coming back to a more general way of rewriting this a little bit later. And this was now acting on the vacuum state, which could be phi 0, as we have defined before, or it could be the Hartree-Fock vacuum. So we're simply changing the vacuum state here. And when we run the equations, what we found yesterday when we used second quantization, when we then required from the variational principle, no, from variational calculus and the variational principle, when we then calculated the expectation value of this quantity here, or rather the transition probability, this is something we want to put to 0, and that gave us an equation which now involves the transition from a one particle, one hole state to the zero particle, zero hole state. And we found that this is given by A, and then we had H0 of I plus, and then we have the sum over the states below the Fermi level. So we have an AJ, and then we have a V, and then an IJ anti-symmetrized. And this is something which we want to put to 0. Now, as we discussed yesterday, there are actually many ways of solving this equation. And the ways of solving this equation is actually to, for instance, set up a type of numerical solution where we could require, when we now look at a general case, we could have P of F of Q, which is equal to an eigenvalue, epsilon, times of P, times the Kronecker delta. So what we are assuming then is that we have defined a solution to this equation, because this equation here actually fulfills the requirement which we have from the variational calculus. So this requirement which you see here is something which we can fulfill by requiring this. And that gave us a set of equations where we end up with, if we have P and F and Q equal to I, this is equal to epsilon I. And then we could have for particle states, F of A equal to epsilon of A. And then we could define a new Hamiltonian, or an effective Hamiltonian, which we label as the Hartree-Fock Hamiltonian, where this acts on a state P, and that gives us an epsilon P of P here. So that means that the new basis is no longer like the previous basis, an eigen basis for H0, but it's actually an eigen basis for a modified one-body Hamiltonian. So this is a one-body Hamiltonian. Now, what it ends up with when we now look at this in terms of this general full configuration interaction theory calculation, what we end up with then is us zeroing out some blocks in the Hamiltonian matrix. So if you now think of a world where we only have zero particle, one hole, and one particle, one hole excitations. So assume now that the full space, assume our Hilbert space, is given by only zero particle, zero hole configurations and one particle, one hole configurations. So these are the only possible states which we can make in our many-body problem. So if that is the case, there is an interesting result which then follows from Hartree-Fock theory. So if we now think of this Hamiltonian matrix which we put up, we can now think of this as blocks here. So we have a zero particle, zero hole block. We have a one particle, one hole block. And then we have the one particle. So this is the original matrix which we have. And we are putting these matrix elements to be different from zero. Then, so this is the pictorial representation of our Hamiltonian matrix. If we assume that these are the only configurations which exist. Now, if that is the case, what we end up with then is that we have a unitary transformation when we perform a Hartree-Fock, where we can now put a subscript HF here. And that leads to a new matrix. And that new matrix, when we perform this transformation, is now going to be given by a block here, where we write an X tilde. And then we zero out this specific contribution. And then we have a new block X tilde here. And we have calculated the matrix elements earlier. So if we now look at the diagonal matrix elements in these specific cases, for these kind of blocks here, so through the fact that we define now A of F of I equal to 0, which is the same as setting phi of HF, the ground state, of H and multiplied with a particle hole state. So when we do the implement the variational calculus on this specific state and look at the variation in the single particle basis, this is what we got yesterday. So this block of matrix elements is equal to 0. And that means that we are actually zeroing out specific blocks. And if the ground state is non-degenerate, if there's only one ground state Slater determinant, then this term here has simply just one matrix element. So let's just write down what this matrix looks like when we have performed the Hartree-Fock calculation. So the way it would look like then, when we have performed the Hartree-Fock calculation, is as follows. So if we take these terms here, so we have 0 here, and then we have this X tilde, and then we have another X tilde. This is now the reference energy. And that is simply going to be given by the following expression, which we also derived yesterday. So we will have I of H0 of I plus 1/2 of Ij, and these are states below the Fermi level, Ij, V, Ij, anti-symmetrized. And this is the same as what we showed yesterday, the epsilon I Hartree-Fock minus 1/2 of Ij, and then we have the same matrix element here, anti-symmetrized. So that's the new reference energy. And that has changed now from the one which we had earlier. So without the Hartree-Fock basis, HF, and where we had defined a basis which was an eigenbasis of these states, mu, Then what we had is that this reference energy, and now we should put a index here where we label that this is the Hartree-Fock. That was given by the sum over mu less than the Fermi level, and then we have mu of H0 of mu plus, and then we have 1/2, and then we have mu of nu, and then we have mu of V of mu anti-symmetrized. So this was the original energy. And what we hope for is that these energies, which we obtain now with the new basis, is an energy which is lower than the original one. So when we use the variational principle, then what we will typically have, if this is the exact energy, this is normally due to the variational principle, since we don't have the exact wave function, we have the energy epsilon 0 of the reference of Hartree-Fock, which is normally less or equal than the original one which we started with. So from now on, my reference energy is 0 ref. In most of the applications which we're going to run in this course, I'm simply going to label that one as my reference energy. So that means that by assumption, I have performed the Hartree-Fock calculation. This is a basic assumption which is often done in many-body physics. When we go to many-body perturbation theory, we are going to switch a little bit between an unperturbed basis and the Hartree-Fock basis. So many-body perturbation theory starts often with not a Hartree-Fock basis, but then you can add a Hartree-Fock basis later. But when we come to other methods like copper cluster theory, we are going to discuss the results in terms of a Hartree-Fock basis, which is, as I mentioned yesterday, is a kind of kitchen item in many-body physics. So if we then go back to the other term which we have here, so we had the ground state in the Hartree-Fock basis, and now we have this block here. So this block contains obviously terms of phi of A, and we can have many such configurations. So this will be a phi of A. So these are the diagonal terms. So we can have hundreds of such configurations, or millions even, because in principle, the particle basis goes to infinity, and that means that we can produce an infinity of one particle, one hole Slater determinants. But these matrix elements here, the diagonal ones, they were given by epsilon A minus epsilon I. So these are the Hartree-Fock energies, which we have. And then we have a two-body interaction which comes in. So we would then have a plus also the reference energy, which kicks in here. And finally, we have two-body matrix elements, which are given by plus. And then we have a sum over J. And then we have an A of J. And then we have a V of I and J here, anti-symmetrized. Now, when we look at the non-diagonal matrix elements, and these are terms which we actually calculated earlier. So when we look at the non-diagonal ones, they will just involve elements of this type, and where J and B are different from A and I. So these are the non-diagonal ones. And the non-diagonal ones were just given by one single integral. And that single integral went like A of J, and then we had a V, and then we had a B of I, or we actually had this term here, anti-symmetrized. So that this is something which we can set up immediately when we are calculating the Hamiltonian here, and the setting of the different matrices. So we would have these blocks, and clearly these blocks actually separate. So if I want the ground state, since we only have one term here, then we have the ground state immediately. And since these do not couple with each other, it means that we can read off the ground state immediately if it's non-degenerate. When we look at the excited states or the states above the ground state, then we would have to diagonalize this block here, because we can have many configurations. So if we have 1,000 one particle, one hole Slater determinants, then these one particle, one hole part of the Hamiltonian matrix would just be 1,000 by 1,000 matrix. But with this unitary transformation, what we have done now is to decouple degrees of freedom. Now, in the general many-body case, we would have a 2-particle, 2-hole here. We would have 3-particle, 3-hole, etc. So that means that there would only be a block of the full Hamiltonian matrix, which gets zeroed out by a specific unitary transformation. So you can think of the Hartree-Fock approximation as a specific unitary transformation in the full configuration theory context. That's the way you should read it. Okay, so yesterday we went through this second quantization type of equations, which is actually very convenient to set up, because what we end up with is, when we look at the equations here, we end up with a practical set of equations which then can be solved. And the way we are going to solve them is to use the connection between the old basis and the new basis I and A here. And we are going to look at the matrix elements of a unitary transformation, and we are going to use the Hartree-Fock method to find the matrix elements of this unitary transformation. And this is essentially what the Hartree-Fock recipe gives us. So the other topic which we are going to study a little bit more in detail is actually the equations for the Hartree-Fock stability. Before we move on, I just wanted to say something about the Hartree-Fock equations in a diagrammatic form. So if we go back to that, let's just write it down here. So Hartree-Fock in diagrammatic form. So what we're having is an equation where we require that A of this operator F of I, and in our case, we identify this as the Hartree-Fock Hamiltonian of I is equal to 0. So diagrammatically and analytically, when we look at the expressions, this is the same as us having kinetic energy, which I wrote like a T here. So T stands for the kinetic energy. And then we have an external potential of I plus this term, which we have J less than Fermi level of AJ of V of IJ. So this is essentially what we have. And when we're now going to set up this diagrammatically or vice versa, what we would have then, if we now take T plus U and X of T, we would then have an outgoing particle line here, A. We have an incoming hole state, I. And then I'm going to write this in terms of a specific vertex here, which involves a one-body operator. So this will be our T plus U of external. And then when I now write out my diagrammatic contribution, what I have is an outgoing particle line, an incoming hole line, and then I have my two-body interaction. But since I'm now summing over the states below the Fermi level, I replace this one with a bubble here, or a loop, with a hole line. And this is the first term. So this is the A and I. We're putting labels on the equations. So this corresponds to AJ of V of IJ. And now I'm not putting the anti-symmetrized term because this is just a direct term and it has a summation over J. So when we sum over states below the Fermi level, we would typically then indicate this with a closed loop. And then we have the next term, which is the exchange term. And we would typically write this out as follows. So we have A here. So there are different ways of writing it. So we would have an I state coming in, and then we would close a loop here like this for the whole state J. And this is going to represent a sum. There's a minus sign when we set up the algebraic expression. There is a minus sign there. We have a J, and we have a V, and now J interchanges place with I. And you see now when you read off the diagram, you have an incoming whole line here, which is on the right side, because we have the I state on the right side. And then the J state here is on the left side, but it also leaves from the right side. So this would be the way we would draw the Hartree-Fock equations. And if you want to write this in a more compact way, if you use these Hugenholz diagrams, you could alternatively write this in the following way. So that means that we have these diagrams, but then what is pretty common then is actually to replace that one with, let me just rewrite that one, the particle state like that. And then we would simply write this in a box like this to indicate that this is a one-body operator. And then we have A and I. And if we then want to use these Hugenholz diagrams, which represent so we have AI and plus, so the Hugenholz diagram represents then an anti-symmetrized interaction. What is common to do then is just to rewrite this one in terms of a blob here, and then we have the particle whole state, A, and then I here, and then you would have a loop here, J. And then we put labels on all the quantities which we have here. So this is a typical way by which we would set up these diagrams here, diagrammatic contribution. And then when you look at the specific contributions, you know that in this diagram here, we have one hole and one loop. So that means that we have a factor which goes like number of holes plus number of loops. So we label that one with an NL and this with an NH. And we know that this one is now minus 1 to the power of 2, which is a plus 1. So that has a plus sign. If we look at this diagram here, we have one hole, but we have 0 loops because this is not seen as a closed loop. And in that case, we get a minus sign. And then if we go back to the analytical expression, which we put up earlier, we see that now that we have a minus sign here for that specific term. So this will be the diagrammatic form of the Hartree-Fock equations. Now, one of the things which we are going to discuss now is the stability of the Hartree-Fock equations. But before we do that, I wanted to set up the recipe for calculating the Hartree-Fock equations, or for solving the Hartree-Fock equation. And the standard recipe which is used, this is the third approach which we discussed yesterday. So the third way of setting up the equation, and which is equivalent to what we have put up before, is then to start with the fact that this state A, and this follows also the exercises this week. So the state A, which we have here, is now given as a linear transformation in terms of a unitary matrix, which has coefficients C, A, mu, and multiplied with our original basis, where now the original basis is typically an eigenbasis for this operator H0. And the basis A is then typically the eigenbasis of this Hartree-Fock operator. So we would put an A of Hartree-Fock here. It doesn't need to be a Hartree-Fock basis. It could be another type of one-body Hamiltonian which is being used. But the standard approach is actually the Hartree-Fock Hamiltonian here. This means that when we now look at the expectation value for the ground state, if we look at the expectation value in terms of a Slater determinant. So we could have a Slater determinant now, which is defined in terms of first quantization. We have 1 over n, and then we would have the wave functions, mu of x1, we have mu1, we have mu2 here. These are all the different states which we can have, and then a mu of n, the states below the Fermi level, which are being filled by the different fermions which we have. And then we would have a phi of mu1, and then we have xn. And this goes all the way down to phi of mu of n of xn here. So this is also relevant for the exercise in this for this week here. So this means that we have defined our Fermi level to contain this specific state mu1, mu2, up to the last one, which is mu of n, which then defines the Fermi level. So this is the original Slater determinant. And then in the exercises last week, you actually used this transformation to find a new Slater determinant. So what comes now is just simply a unitary transformation, and where we expand a new basis in terms of the old basis. And that gives us a new Slater determinant. But when we then impose through variational calculus the conditions which result from Hartree-Fock theory, then we have a recipe for actually calculating these states here. But these states are assumed to be given by a linear combination of these original states, which we have. And these original states were often chosen because we think they are physically relevant, they are good approximation to the system, and an equally important aspect is that we can define these states in terms of the eigenvalues of this operator H0. And what happens in some circumstances is that the integrals we end up with in this basis here can be solved easily, or they may have even analytical expressions, or they can be solved numerically in an easy way. So this is the kind of basic approach which, motivates the introduction of a specific basis. And when you have that one, you have an orthogonal basis, which you then can use to define a new basis. And in our case, the new basis is going to be the solution of that problem. So the next Slater determinant, which we then would have, would be this phi 0. And now I just write it as a Hartree-Fock state. And that in first quantization is going to be given by 1 over n. And then I'm going to have a new state. And I'm going to label this with an A1. And then I have an A2 all the way up to an AN. And then I have X1, X2, no, X1 all the way down to X1. And then I have a similar one here, phi. These are the quantum numbers which fill up to the Fermi level. And we have used the letters I, J, K, and L to indicate the states below the Fermi level. But this is set up now in first quantization. And then we would have states like this explicit A1, A2, up to AN, which now define the Fermi level. So that's the ansatz. And then what we can do, and this is also one of the tasks in the exercise, is to set up the expectation value of the energy. So we can actually calculate the expectation value of the energy with the original basis. And we know the expression for that because we've showed it. And this is going to be given by a sum over the basis here, where this now runs up to the Fermi level. And it's going to be given by mu of H0 of mu plus 1/2 of mu. And then I have mu V of mu. And this is the anti-symmetrized result. So this is the expectation value in that specific, with that specific Slater determinant. And we have calculated this. In the exercise, I'm just asking you to convince yourself that this is the case again. And then we can set up the similar expression with a new basis which we have, with the Hartree-Fock basis, or where we have the Roman letters. So this would be the reference energy in the Hartree-Fock case. And this has a similar expression, which we can write as A, but now we're going to change it back to the notation which we are used to. So I'm going to rewrite this one in terms of I less than F. And now I'm going to have an I of H0 of I plus 1/2. And then I have an Ij, and then Ij V of Ij anti-symmetrized. Now what I can do next now is I can rewrite this basis I, and we know that this basis I is given by a summation over all the possible states which exist. So I'm going to write this as a state lambda. So lambda is not restricted to be only states below the Fermi level. So not restricted to be below the Fermi level. So in principle, this lambda runs over all the basis functions which we have, which in principle, again, given by an infinite sum. So we would then have an overlap coefficient, Ci lambda, and then I would have my state lambda here, where we have assumed that these states lambda are eigenstates of this operator here. So in principle, lambda runs from 0 to infinity, but we will make a truncation there, and that will define the active space which we have with whole states and particle states. So if we then insert that in the equations, if we now look at this term here, we can now rewrite that one, and this is where we're going to stop before we take a break. So there's going to be a sum I less than F, and this sum runs over the particles below the Fermi level. So you will often see this indicated as a density-dependent term. And if I now plug it in here, I'm going to have a summation over mu and nu, because I'm inserting these coefficients. So I will have a C I nu, and this is complex conjugate. And then I have a C of I of nu. And then I have a contribution here which goes like mu of H0 times nu. Does that sound reasonable? So I'm simply just inserting the expressions for the state I here and the other state I in terms of the expansion which we have made here. And then you see now that the second term which we have is going to give us a quadruple summation over different Greek letters. So that means that I'm going to get an additional term, and that's the last thing we're going to set up before we take a small break. So the expression which we end up then with is a term plus. So we have a plus 1/2. And then there's going to be a summation over I and j below the Fermi level. So this sum is restricted to the number of particles which are present. But then the next sum, when we are setting in this old basis, that is not restricted to terms below the Fermi level only. That runs over all the single particle states which we have. So just to remind you that when I used my old function here, my old basis, this sum is also restricted to the states below the Fermi level, because that follows from the way we have set up this Slater determinant here. So in the old basis, I'm also having something which I normally call a density-dependent contribution, because it depends on the density of states below the Fermi level. So we normally call this a density-dependent contribution or particle-dependent contribution, because you would then, this corresponds to us summing up to the number of particles which we have. And I would get the same here when I just change bases. And when I do this changes now, and I need now to have a sum over alpha and beta and mu and gamma. So these are not restricted. And in principle, they run up to infinity. To be below F. So I'm going to get a coefficient which goes like Ci alpha, complex conjugate, Cj beta, complex conjugate. I'm going to get a C of I of mu. I'm going to get a C of j of mu. And then finally, this is going to be multiplied with this integral here, mu. Let me just rewrite it. I have alpha, beta, and then V of mu and nu anti-symmetrized. So let me frame in the quantities which then hopefully can be calculated. So this can often be calculated in a handy way. I'm putting quotation marks here, easily calculated. Calculated and then tabulated. And tabulated. So in the midterm, which we are going to discuss next week, these integrals are going to be replaced by a constant. So that makes life very easy for us. But in principle, if you have, let's say, a harmonic oscillator basis, or you have a Gaussian basis or whatever, then you have to evaluate the integrals. And that clearly can be cumbersome, it can take time. But the idea then is that if you can handle a large single particle basis, you will typically pre-calculate these matrix elements and then store them. And then when you run your Hartree-Fock calculation, you would simply just look them up with the indices alpha and beta and gamma and mu. So you will have a table which you just look up. And after the break, what we are going to do is just to vary these parameters, which you see here. So we are not going to vary these terms, that's fixed, but we're going to vary these parameters here. And that is going to give us the same type of equations which we derived in second quantization or first quantization yesterday. Then the other thing is that if you look at the term which you also have here, this one, that can also be pre-calculated. And often this has an analytical expression. If it's an harmonic oscillator potential and you use a harmonic oscillator basis, then we know exactly what this is. It has a simple analytical expression. So you would also pre-calculate that one and store it. And then we are going to set up an equation now, which is going to be an eigenvalue equation, where the thing which we need to do then is simply to solve an eigenvalue equation where these unknown coefficients are the eigenvectors in the expansion which we have defined here. So that's the typical way you would solve the Hartree-Fock equations from a practical point of view. For those of you who may encounter density functional theory, the equations are going to be the same, except then that there will be approximations to this term here. But the practical recipe which we have for Hartree-Fock theory is going to be the same practical recipe which you will have in density functional theory. Okay, I went a little bit over time because we start a bit later. So after the break, we are going to use this third approach, and then we're going to set up a practical recipe for finding the Hartree-Fock solutions. And you're going to use that one in the midterm as well. And after that, we are going to look at the stability of the Hartree-Fock equations, which will also be useful in the midterm, because in the midterm, we are going to find a condition on the matrix elements, which we have here, which will be given by constants, a condition for the stability of the Hartree-Fock equations. We'll take a small break. Is that okay? Just stretch legs and grab some coffee. or water or whatever. Before we look at the practical derivation of the Hartree-Fock equations, which are going to be the equations we will solve numerically, I just wanted to say something about what is going to come. So next week, when we're also discussing the stability of the Hartree-Fock equations, we are going to introduce a new system. And this is a system which has been widely studied in condensed matter physics. And it's called the infinite homogeneous electron gas. And this is a model which has been extremely successful in explaining, let's say, the conductivity properties of semiconductors, for instance. And some of you may have heard of the electron gas, the homogeneous electron gas. One of the things which is nice with the electron gas is that we can actually solve the Hartree-Fock equations analytically. And that's extremely beneficial. And we can find the contribution to this Hartree-Fock energy, which we have tabulated here. We actually have an analytical expression for the electron gas. But there is more. There is more because the electron gas has served as an approximation to the way we solve the density functional theory equations. So we are going to use the electron gas not only to study a specific system where we can obtain analytical solution and perhaps gain some more intuition about the system, but we are also going to motivate the first type of approximation which is used to solve the equation for density functional theory. So in density functional theory, and this is something we will do next week, we are going to rewrite these in terms of the density of the system, which is a very common way of doing that. But then the problem with density functional theory, which then expresses these same equations in terms of the densities, is that due to the Pauli principle, we will have an exchange term which is non-linear in the density. So from a practical point of view then, people have introduced an approximation to the exchange term due to the Pauli principle, and that's called the local approximation. And that allows us to set up a recipe for calculating the density functional theory equations for a single particle, and they are going to be lookalikes of what comes now for Hartree-Fock theory. So the equations we're going to set up now can be reused when we do our first practical density functional theory calculation, where we approximate the exchange term. So remember now that when we looked at the equations for the Hartree-Fock terms, we have a direct term, which is given by this term here. And when we rewrite this in terms of densities, we are going to have two terms which are linear in the density. But then all the evil stuff is in the exchange term, and that is a term which will be non-linear in the density. And the local density approximation is obviously an approximation, which then tries to approximate this term here. And the approximation comes from the electron gas. So the electron gas serves as an approximation to solving density functional theory equations. So these are things which are going to come. But first we have actually to set up the equations. So I just wanted to motivate a little bit the kind of steps which we're going to take so that you will see how you can also use this formalism to solve the Hartree-Fock, the density functional theory equations. So let's now go back to this functional. So we have the energy here in terms of these coefficients, and we are now going to vary these coefficients. So these are the quantities which we are going to use in variational calculus. So let's bring this up. So let's just set up variational calculus. So there's another thing which we need to look at. So we have assumed now that this new Slater determinant for the ground state is also normalized to 1. This is a basic assumption which we are making about the Slater determinants. If we look at the basis which we have defined, this IJ basis, or the Roman letters, this overlap here for the single particle state is actually given by a summation over alpha and beta. And then I have a CA alpha over CJ beta. And then I have my overlap with alpha and beta. Now that basis alpha and beta is also assumed to be an orthonormal basis because these C's are matrix elements of a unitary transformation. And we know that if we perform a unitary transformation on a basis, the new basis, if the previous one was orthonormal, the new basis will also be orthonormal. So this simply reduces due to the fact that we have a Kronecker delta to delta alpha beta here. And that limits the sum just to one of these variables. And then we can simply rewrite this in terms of this quantity which you have here. But I'm going to keep the Ci alphas with a complex conjugation as well in the equations. Then, if I do my Slater determinant, the Slater determinant will then contain a sum over the particles. So it's pretty easy to see that the normalization condition here, Hartree-Fock, becomes simply a summation over the number of particles, I equal 1 up to n. This is the number of states which are occupied below the Fermi level. And since we have n particles, this has to reflect the number of particles. And that's where we'll get this density-dependent term. And then I have a summation over alpha. And then I'm going to rewrite it like this. Okay. So when I'm setting up my variational calculus, I'm going to define a functional f, which is a function of the Hartree-Fock trial state for the ground state. And that will be given by the energy, which we calculated in the previous lecture. And that's given by the equations which we had here. So this term here. And then we need to subtract this term with a Lagrangian multiplier. So there will be a sum over I equal 1 up to n. There's going to be a sum alpha. And then we will have this multiplier here, Ci alpha. And then there's going to be a Ci alpha of Ci alpha here. So this is our Lagrange multiplier. And this is the typical way by which we now implement the variational calculus. So what we're going to do now is to vary this function in terms of variations in the parameters C. And then that is going to give us a set of equations which we then can solve numerically. So if we then perform the calculations here, what we need to do now is simply to calculate the change in this function, Hartree-Fock, with respect to these parameters Ci alpha. And it is sufficient to look at the complex conjugated terms because they will be independent from the equations which follow for the non-conjugate complex term. So it's sufficient to look at this equation here. So what we need to do now is to take the derivatives for these coefficients Ci of alpha. So what I'm going to calculate now is this Ci alpha. And now I'm going to set up the equation so you can see exactly what we end up doing. So we are going to have a sum here. And now we are picking one of the coefficients. So if you go back to the expressions which we had also for the energy here, you see now that there is a term here, for instance, the term here, which runs over Ci alpha, J beta, etc., etc. There will be one term, so we isolate one of these sums here. So that means that we are only looking at 3 of these sum variables. And we are picking one of these. And we are picking one of the i's here. And that means that we will get a series of terms for I and alpha, which will then set up the final equations. So you can think of this as a matrix which we're going to determine pretty soon, where we will then pick every row for given coefficient I here, for given variable I. So we now pick one of these is I alpha combinations. So that means that outside here, there is a sum over I and alpha. So just keep that in mind, right? So we are going now to calculate the derivatives. So we will have a C, and we are going to make another assumption here. If you look at this specific term, one of the standard assumptions which is being used is that this H0 has this nu and alphas, etc., as an eigenbasis. So that means that this term is just going to be given by a term which now reduces to a sum over just one of the coefficients, or one of the variables, mu and u. So what I will have then, when I'm setting it up, there's going to be a term which goes like, so I will have a Ci alpha, and then I will have the epsilon alpha, which is simply this integral over H0 of alpha. We will now have assumed that these alphas are eigenstates of H0. That's a very common approximation which is made. We don't need to do that, but I'm going to do that because that will simplify the equations here. And then we need now to look at the interaction term, which goes like 1/2. And I picked one of the i's, so I have isolated. So just keep that in mind. I have isolated I and alpha. So that's why I'm taking away these summations. And then I have plus, and this contains now a sum over j. And there is going to be a term Ci alpha, Cj beta, complex conjugate. And then I'm going to have a Ci, and I'm going to call this gamma, and Cj delta. And I will have an integral here of alpha, beta, V, and gamma delta, anti-symmetrized. And then I have these coefficients minus epsilon I alpha multiplied with Ci alpha of Ci alpha. And I want this one to be 0. Okay? So when I take the derivative, I mean, the first term is pretty easy. So that gives me Ci alpha times epsilon alpha. But then when it comes to the second term, I have to be a little bit careful because these terms j and beta can also have a combination of I and alpha. So I have an explicit I and alpha here, but now I'm summing over j here, and I forgot actually to put up an additional sum. So there should be a sum over beta, gamma, and delta. So I have isolated the alpha sum. So that means that I have a sum over beta, gamma, and delta, but the beta could also be equal to alpha, and j could also be equal to alpha. So I actually have to take the derivative with respect to this term, but I also have to pay attention to that term. And doing that is going to take away this term 1/2. So the thing which will then happen is that also because the matrix elements, since these are dummy variables, I can always change the interchange alpha and beta and gamma and delta. So at the end, what we are going to get here when I set up the equation, so just keep that in mind, that I need to take the derivative with respect to that, and also that one. So that will take away the term over 1/2. So I will get one term here where I have the derivative with respect to that. And then I just interchange beta and alpha because these are just dummy variables, and the same with gamma and delta. And then we are going to get an equation which is going to look as follows. So I will get an equation where I have Ci alpha multiplied with epsilon alpha. I'm going to get a plus, and I have a sum over j equal 1 up to the number of particles. And then I'm going to have a sum over beta, gamma, and delta. And then I'm going to have a C J beta. And then there will be a C gamma of delta, and so C of I like this, and Cj of delta. And there's going to be a matrix element which runs like a alpha of beta of V of gamma and delta. And this contains a minus. And then I should rewrite this. I should be a little bit careful here because this epsilon here is an epsilon I alpha. So this is the Lagrange parameter minus epsilon I alpha times Ci alpha. And I want this to be 0. So when I reorganize this equation here, so let me now bring up the slides again, because then we are also going to discuss how we will solve this in a practical terms numerically. So let me switch from the whiteboard to the slides again, because then we will also discuss the way we were going to set up these equations numerically. So what you will see here is essentially the same thing which we had on the whiteboard. So you can then change the summation labels. So we would have this term here. So this is what we end up with, these terms here. And then we can then rewrite everything, as you can see here, with an outer sum of a beta. So we can isolate that one. And then, because these are just dummy variables and we can call them whatever we want. And here what I did was to keep, so let's just rewrite, we can rewrite the equation we had and not assuming that this one is diagonal in alpha and beta. So let's keep that. So then we have the outer sum beta, which we isolate here. And we have the coefficient Ci beta. And then we have the coefficients here because we can always interchange these terms, which you see here, because we can rewrite this equation because these are just dummy variables. So that means that when you look at this expression, which you see here, you can interchange. So you have a beta here. And as you see now in the equations, what I've done is simply to interchange gamma with beta. These are dummy variables, so you can call them whatever you want. So I interchange beta and gamma here. So you see I have beta here, and then I have gamma here. And that means that my coefficients, which previously had a Cj beta, becomes a Cj gamma. And then I isolate Ci beta here. So these are just interchanging symbols. And that means that what I end up with is something which I can write out in a compact way with these coefficients here, multiplied with this set of integrals, which now normally allows us, if beta is an eigenbasis of little h, then this will be only given by some epsilon of alpha and a Kronecker delta. And then I have this summation here. And this is something which I can then rewrite in a more compact form as an operator here, multiply with these coefficients. This actually becomes a matrix, what you have here, multiply with the coefficients, and you see that this is just nothing but an eigenvalue problem in the unknown coefficient C. So this is essentially us using the variational, the calculational rules from variational calculus, and then we end up setting up a problem which then can be solved by numerical solution of an eigenvalue problem. And the eigenvectors give us these coefficients Ci beta and Ci alpha. And then we can start solving the problem. And the problem is that when you look at the equations here, we don't know these coefficients. That's our problem. And you see that this matrix here has a nonlinear dependence on the unknown coefficients. So what we need then is actually to set up a guess for these coefficients. And that's the standard way by which we start the Hartree-Fock calculations. So what you would guess on then is that in the beginning, you could now guess that these coefficients are just 1 and given only by the diagonal elements. And that's a typical guess for a Hartree-Fock calculation. So that means that when you're setting up the recipe now, you would rewrite this in terms of a matrix, the Hartree-Fock matrix. You multiply that with the eigenvector, which now contains these coefficients. And then you have the eigenvalues, the Hartree-Fock eigenvalues, times the eigenvectors. So you would typically start with a guess for these coefficients, and you can simply set them equal to the diagonal elements only. So this would be your 0th iteration. This is a standard way people would solve the Hartree-Fock equations. Then, if you do that, then this would just reduce to a sum over j equal 1 up to n, because this would just contain the diagonal contributions then. So that means that gamma is equal to j and delta is equal to j. That would be the first iteration. And then you have just the contributions from this integral, which you can look up in a table, and then you would simply sum over the j values here. Then, when you have this matrix, then you go back in here and you set up the matrix to diagonalize, because now you have the matrix and then you diagonalize it. Now, diagonalizing it gives you new coefficient C and a new energy. Then you use these new coefficients to recalculate this matrix. And then you continue till these energies don't change by a predefined tolerance which you set. So you would typically then, with the new eigenvalues, you can set up a new Hartree-Fock potential like this. And then you would recalculate. And then the diagonalization with the new Hartree-Fock potential yields new eigenvectors and eigenvalues. And you would continue this process till you have reached your tolerance criteria. This is the basic recipe for performing a Hartree-Fock calculation. And next week and the week thereafter, we will discuss implementations of the Hartree-Fock algorithm. But we need also to understand the stability of the equations, which is also equally useful because we can relate the Hartree-Fock equations to the matrix elements of the interaction, and we can say something about the stability of this iterative process here. Because it's not guaranteed that this iterative process converges. It's not given. And the next thing which we're going to do now is actually to look at the stability of the Hartree-Fock equations. Any questions? Does this sound, I mean, the equations here, these are the, is it just a rewrite of the equations? And if we solve this problem here, that corresponds to the same thing which we set up yesterday, the same equations for solving the Hartree-Fock problem, which we did in second quantization. So this is just another way of solving the equations which we derived in second quantization. Yeah? Yeah. So what you're saying is that if we have this specific guess in the beginning, then we risk that we may have matrix elements which are 0. Is that what you meant?
No, in the derivation, when we did the variation,
yeah,
the variation on the sum,
yeah,
by a,
yeah,
and that sum is equal to 0, which you
yeah,
say that each element of that sum is 0. That's what you
okay, let me see if I understand your question properly here, because let me switch to the whiteboard here. And let me see if I understand properly the question, because with a headset on, sometimes I don't hear properly. So what we had, when you're thinking of what we had yesterday, right? Yeah.
Yes.
Yeah. Or so I'm just picking one specific coefficient, but you will have to do this for all the coefficients.
Yes, but do we know that each term of the sums of I and j are equal to 0? Because there could be solutions where the terms are not equal to 0, but they cancel. Is that important?
I need to think of that. I don't have a clear immediate answer to that. Because what we end up with here is just having defined this Hartree-Fock matrix, alpha, beta. So now just writing it in terms of the specific matrix elements. What you have is when you perform the derivations, you get this term here, plus the sum over j equal 1 up to n. And then there is a sum over gamma delta, which runs freely. And then I have a c I of gamma, complex conjugate. And then I have a c of j of delta. And then I have a matrix element of alpha. And then I have gamma. And then I have v. And then I have a beta of delta. So this is just that matrix. And then what you end up solving is this problem here, where you now sum. And let me just quickly remind myself of what we had here. So you have a sum over these betas. Cij, so this should be a j here, actually, j there. So then you have a sum over the h alpha beta. This is just a matrix. And this is multiplied with ci beta. And that's equal to this epsilon I Hartree-Fock of ci alpha. So the equations which you, when you look at, so let me just bring it up again. When you look at the expressions here, this now runs over all the betas, and you would have over all the i's. Because in the derivation here, I picked out one I and one specific alpha. But this equation here, when you set it up in terms of a matrix problem, you would simply have this H Hartree-Fock multiplied with this vector, and then you have some eigen energy multiplied with C here. And these C's contain all the Ci alphas. And this is just a matrix multiplied with a vector. So in a sense, you have all the coefficients. And there may be a term which could be 0, but I don't think that causes a problem here. Because you can have terms which are 0, but that is because of specific symmetries which are conserved. So if you have a spin symmetry which is obeyed, then if you try to put together matrix elements with a spin half, spin up, and a spin down, these matrix elements will be 0. Is that what? Because in the sums here, there will be 0 contributions. Is that something? Is that more close to what you were thinking of? Because you can have zeros here. Because your Hamiltonian has some specific symmetries which are obeyed. And then you could actually have specific contributions which have to be 0. So just to give you an example here, I think this is a very good question, because I didn't want to say anything about symmetry conservations. So when you're setting up this Hartree-Fock matrix, there are some constraints here. So if you look at this term here, for instance, this term has 2 states here. And if this H0 doesn't change spin, then I cannot connect a state with a spin up here with a state with a spin down here. So that will be 0. The same thing will happen here. So you can set up these states in a random order, and then you will have a Hamiltonian matrix which will be put up in a random order. However, when you diagonalize, the thing which is nice then, when you diagonalize it, the Hamiltonian itself will figure out which one should be 0 or not. So if you have a Hamiltonian which obeys a specific symmetry, even if you set up the matrix elements here in a random order, the right symmetries will come out if you have encoded them properly here and properly here. But what you would do then to reduce the dimensionality, if these operators here do not act on spin, you can separate it in a block with spin up states and a block with spin down states. And if there are no differences between spin up and spin down, it is sufficient then to diagonalize the block with spin up. And that can reduce the dimensionality of the problem with a factor of 2. Or alternatively, you can just set up these matrix elements in a random way. So that means that you would have one with spin up and one with spin down here, which would be 0. So there will be scattered 0. But then you would typically have that when you diagonalize, that the right symmetry comes out. But just to give you an example here, if you now think of a system with 2 doubly degenerate states, so you would have a spin up here and a spin down here. So this is just, and a spin up here and a spin down here. And you would label this as a 1, 2, 3, and 4. So when you run the Hartree-Fock calculation, then what you would see then is that the matrix elements of the Hartree-Fock matrix, that will be 0. So if you have an odd state, which you have labeled as a spin up state, and an even state, which is labeled as a spin down, then you could actually rewrite everything in terms of the odd guys only, 1, and then you would have 1, and Hartree-Fock of 3, and then you would have 3, H Hartree-Fock 3, and then you can set up a matrix which is a 2 by 2 matrix, instead of you having a 4 by 4 matrix, because you have 4 states here. So you could have a block with a 2 by 2 for the spin up, and a block of 2 by 2 for the spin down. So your Hartree-Fock matrix in that case would look something like this. You would have this block 1 of Hartree-Fock 1, and then you would have 1 Hartree-Fock 3. So that would be one of the blocks, and then you would have the emission conjugate of that one, and then you would have 3 of H Hartree-Fock of 3. So that would be one block, and there will be a similar block for the spin down states. And they don't connect because the matrix elements are 0. Alternatively, you could just run in a random order with spin up and spin down, but you would still, when you diagonalize, the symmetries of the Hamiltonian would kick in. That's always a useful test that you have set up the Hamiltonian correctly. So you can have matrix elements which are 0 there. But that is something which follows the symmetry of the problem. Now, what I wanted to do now is actually to look at the stability of the Hartree-Fock solution. And we will most likely start with that next week. But let me just say one thing here, which we are going to use. There's one thing which we actually didn't discuss. So when we run the Hartree-Fock calculation, the thing is that the variational conditions which we have and the variational calculus recipe which we have applied, that guarantees only that the expectation value is an extremal value. It doesn't say anything of whether this is a minimal value or a maximum value. So we have no guarantee whether it's a minimum maximum. So what we need now, in order to discuss the stability of the Hartree-Fock method, is to introduce a theorem. And this theorem is called Fowler's theorem. And that gives us a general representation of a Slater determinant in terms of one particle, one hole excitations. And this is what we used yesterday to derive the Hartree-Fock equations in second quantization. So what we need to show is something which will then depend on Fowler's theorem. And I'm just going to state it, and this is where we will stop. So Fowler's theorem states that we can actually rewrite any such Slater determinant in terms of the following expression. So let me just set that up, because that's in principle what we used yesterday and which we motivated in a more ad hoc way. So a general Slater determinant, or a random, or just a general Slater determinant, SD, which I'm just going to call a phi prime, that can be which is not orthogonal. So that's an important condition, not orthogonal to another Slater determinant, and that could be over phi 0, the one we started with. And this phi 0 is something which we wrote in terms of the states which are present up to the Fermi level. And then we have the AI acting on the true vacuum. That Slater determinant can actually be written, and we are going to show that next week, that can be rewritten as an exponential. And this is where we stop today. And there's going to be a sum over the states above the Fermi level, a sum over the states below the Fermi level, the whole states. There is going to be a coefficient CIA, and then we have an AI, and AI, sorry for that, multiplied with this phi 0. We actually used that yesterday to derive the Hartree-Fock equations. And then what I stated was that the variation of the delta Hartree-Fock state was given by something which went like AI dagger, AI, acting on phi 0. I just motivated that in a kind of ad hoc way. Now, Thule's theorem says that you can rewrite a Slater determinant in this more general way. And next week, we are going to prove that. And we need this to show the stability of the Hartree-Fock equations. So what I'm going to give you also next week when we discuss the stability of the equations is a more sounder motivation for why we had this specific approximation when we looked at the derivation of the Hartree-Fock equations. So the derivation of the Hartree-Fock equation in second quantization simply start with Thule's theorem, which says that a general Slater determinant can actually be written in terms of a linear combination of particle-hole excitations. And that's an extremely useful theorem because one, it motivates and shows the second quantization derivation of the Hartree-Fock equation. And at the same time, we're going to use this to study the stability of the Hartree-Fock solution, which you will need in the midterm, which we're going to discuss next week as well. So this is like me presenting, it's just like when you see this TV series, you cannot wait for the next episode, right? And this is where we stop today. Yeah. Yeah. Yeah.
So this will give us like few hole.
No, it's actually going to stop at the order one particle, one hole. Yes, and I'm going to show that next week. That's a very good question, actually. When you calculate expectation values, but what is normally done here is that you would truncate it when you implement it. And then you would simply, what you would add then would actually be a small permutation or perturbation of these coefficients. And then you would stop at the first order expansion in your Taylor expansion. And that's what motivates that one. That's a good question. Yeah. Yeah.
So we can refer to what's the shortcomings of the Hartree-Fock method?
The shortcoming is that if the interaction is strong, it may not converge. That's the main shortcoming. So if the interaction is strong, if you go back to this very simple picture which we had in the previous lecture, if you look at the approximation which we made here, where we simply assumed that life consists only on 0 particle, 0 hole, and 1 particle, 1 hole determinants, then Hartree-Fock would simply tell you that I can find a unitary transformation which zeroes out the cross terms. However, you have 2 particle, 2 hole here, etc., etc. And if the interaction is strong, these contributions can be large. And also the Hartree-Fock then may not actually converge in the iterative process, may not converge. And that depends very much on the relation between interaction and the external confining potential. So if the mean field is meaningful, that is simply because the contribution from these guys here are less important than the one from the potential which confines the motion of the particle. If the mean field is a good approximation, then everything we have done with defining these single particle states is meaningful. If you have a strongly correlated system, then everything breaks down. So if you're studying the phase transition of superfluid helium to normal fluid helium, then that is a case where everything we have done till now breaks down. And the nice thing with the stability of the Hartree-Fock equation, and also the project with the Lipkin model, which we will have as a first midterm, is that you can find analytical expressions for the condition on the stability of the Hartree-Fock equations in terms of the interaction. Okay, I'm going to stop here now.